the first two parts of this tutorial, I set up and solved this model of a fuse. I sent a current through it, and the Kامsól computed the temperature increase. In this part, we'll find out how you can improve the simulation by introducing temperature-dependent material properties. Let's get straight to the materials and have a look at what I used last time. So we have Fr4, copper, and aluminum. The fuse itself is made out of aluminum, so that's what I'll focus on. You can see here what properties we have assumed for this aluminum. There's, for example, the heat capacity equal to 900 Joule per kilogram in Kelvin and so forth. These properties are all constant values. Keep in mind especially that we have an electric conductivity of roughly 3.8 times 10 to the 7th Siemens per meter. This happens to be a perfectly fine value for aluminum at room temperature. Now what happens in reality when we heat it up is a whole different story, and we should capture that in the model. So let me see if I can find a more extensive version of aluminum in our material library. I'll browse down to Material Library, Elements, and scrolling down just a little bit, we'll find aluminum. Let me add that to the model and apply it to the same domains where we had the old version of aluminum before, the version with just constant material properties. You'll notice that we no longer have constant values for these properties. Instead, we have these funky-looking expressions. What are they? Well, let's find out. For example, the electrical conductivity is now specified as this piecewise function. We'll focus on the part of the function that is for the relevant range of temperatures from 200 up to melting point. And I'll plot that. So what does that look like? Well, remember that we had this constant conductivity of 3.8 times 10 to the 7th at room temperature. And that's what we see here too, just below 300 Kelvin, right? This is the temperature and this is the conductivity. Now for higher temperatures, the conductivity decreases quite rapidly, and we actually end up at less than 1 times 10 to the 7th just before melting. So this is quite a difference versus what we had before, and we should adapt the current to that. So before, with this constant conductivity, we needed a 15 amp current to melt the fuse. Now that we take into account the decreased conductivity at higher temperatures, this should mean that we will need less current before it melts. Right? Well, that's something you may want to think about for a second. But let's just try it out. I'll send in 9 amps instead of 15 amps as we had before. So I'll just browse down to the terminal button and I'll send in 9 amps instead of 15 amps, and we'll solve the model again by clicking Compute. And we have the result. A temperature distribution with a maximum just below 900 Kelvin, which is just a little tiny bit less than the melting point. So making this a two-way coupled multiphysics model, taking into account the true material dependency on the temperature, turned this presumed 15 amp fuse into something closer to a 9 amp fuse. That's quite remarkable.